Okay, this video is about an interesting method that I stumbled upon for balancing chemical equations. I have not seen this method anywhere before, but I seriously doubt that I'm the first to discover this technique. So let me go through an example here and show you how I do this. And then I will have some follow-on videos to talk about it in a little bit more detail. Okay, the assumption here is that you are somewhat familiar with solving systems of linear equations and matrix manipulation. So this would be sort of an algebra 2 level of mathematics. And let's see how I pull this all together. Okay, I'm going to begin with these four chemical compounds. So these are the input compounds, the compounds that react together to form these two compounds right here. And I have to figure out how much of each compound is needed to make this all work out. So we have the same number of sodium atoms on both sides of the equation, same number of oxygen atoms, same number of hydrogen, same number of sulfur. You get the idea. I'm assuming you already have some familiarity with the concept of balancing chemical equations. Now, this equation is not too terribly complicated, so you could probably solve it without employing this technique. But the neat thing about this technique is that it should work no matter how complicated your chemical equation is that you need to balance. So here's the way I go about it. Okay, I begin by writing my input, my reactant compounds on the left-hand side, and my output compounds on the right-hand side. And I represent each compound here by a vector. So NaOH is vector A, H2SO4 is vector B, Na2SO4 is vector C, and H2O is vector D. Now the idea is I need to find integers to multiply each compound to make everything balance out. Okay? So with that in mind here, so here's what I do. With these vectors now written down across, now down on the vertical columns, I write all my elements that appear in the equation. So I just write them down in order that they appear. Here's sodium, here's oxygen, here's hydrogen, and here's sulfur. So these are the four elements that appear in these four compounds. And then in this box here, these boxes, I write down how much of each element appears in each compound. So there's one sodium atom here, there's one oxygen atom here, and there's one hydrogen atom here. There are no sulfur atoms. Over here, there are no sodium. This is the sodium row. There are no sodium. There are 4 oxygen. There are 2 hydrogen right here, and there's 1 sulfur. So you get the idea. 2 sodium, 4 oxygen, 0 hydrogen, 1 sulfur, 0 sodium, 1 oxygen, 2 hydrogen, 0 sulfur. So that's not too complicated. So as I said, the problem is then to find out the integer values A, B, C, and D, such that A times A vector plus B times B vector is equal to C times C vector plus D times D vector, where the red lowercase numbers are scalars in my vector equation. Now this equation right here, this one going all the way across here, this must be satisfied by each row in this array right here. So it must be satisfied by the top row, second row, third row, and fourth row. So I now write out each row here, if you like, of this equation, this one right here. I write out each row. So I have the sodium row. it gives me that A plus 0 is equal to 2C plus 0. Where does that come from? A plus 0 is equal to 2C plus 0. And the next one, the oxygen row, A plus 4B is equal to 4C plus D. So I have A plus 4B is equal to 4C plus D, and so on. I write this down for the hydrogen row shown here and for the sulfur row shown here. Okay, so I now have a system of 4 simultaneous linear equations that must be satisfied by my constants A, B, C, and D, and I need to solve these 4 equations for the constants A, B, C, and D. So this is pretty much a traditional problem in algebra, system of linear equations and how to solve it. I do have some restrictions, and that is I want A, B, C, and D to be integer valued because I'm not going to take a fraction of a compound, a fraction of an atom. And so I need those to be integers. Now, potentially here, this seems like to me like it can be solved by using something called integer programming. But I'm not going to go into that, and I don't think we need to go into that. Now, something let me also mention here, in that once we find a solution to the chemical equations, we find A, B, C, and D, we can take all those values for A, B, C, and D, multiply all those values by 2, for instance, and those new multiplied by 2 values also solve the chemical equation. So in fact, generally speaking here, there are an infinite number of solutions to balancing a chemical equation, and what we're interested in is finding the smallest integer values A, B, C, and D that solve this system of linear equations. Okay, so let's continue here with this. Okay, I take everything that's on the right side and I bring it over to the left side. So everything that's over here on the right side, I just subtract 2C plus 0. So I subtract 2C from both sides of the equation. I subtract 4C and I subtract D from both sides of the equation. And I subtract 2D and C from both sides of the equation. So this gives me this set of simultaneous linear equations. And I could write this now, written in this form. This is a set of homogeneous linear equations. So if you want to look up mathematically how to solve this, you might look on Wikipedia for homogeneous linear equations. And it's homogeneous because I have all zeros on the right-hand side. Okay, so here's my matrix equation then. I write this set of linear equations using a matrix formulation, and this is what it is. Notice that what this means is I have 1 times A plus 0 times B minus 2 times C plus 0 times D equal to 0. I have 1 times A plus 4 times B minus 4 times C plus D equal to 0. See, so that's a way of writing out each equation using this matrix times my vector of unknowns, A, B, C, D, and I'm saying it's all equal to 0. Now, there's one obvious solution, and that's if I set A, B, C, and D all equal to 0, that solves the equation, but that's called the trivial solution, and that really doesn't answer my question. While those values solve the equation, I'm interested in values of A, B, C, and D, which are generally not 0. And in fact, remember, as I've said, they need to be integer valued, and A, B, and C, and D also must be non-negative. Okay, so here's what we have here. Now, the idea in solving this type of matrix equation is to put it in something that's called upper triangular form. And I do that, and again, I'm assuming you have some familiarity with that, so I'm not going to explain how that is done. I'm just going to talk about what I do here. So I have this times this is equal to 0. So I'm going to try to put it here in upper triangular form. So I'm going to take row 2. This is what I mean here. I say row 2 minus row 1. And I'm going to put the answer into row 2. So row 2 is this, 1, 4, negative 4, 1. Row 1 is this. I'm going to take this, subtract these numbers from it. So 1 from 1 is 0. 0 from 4 is 4. Negative 2, subtracted that from negative 4 gives me negative 2. And 0 from 1 gives me 1. I'm going to take those answers and put them back into row 2. So here's my new row 2. I'm going to take row 3 and subtract row 1 from it and put that into row 3. So here's row 3. I subtract this row from it, term by term, 1 from 1, 0 from new. I subtract negative 2 from 0 and 0 from negative 2. And I put that answer into row 3. So here's my new row 2, and here's my new row 3. Okay, now I'm going to continue playing around with this. I'm going to take row 3 from up here, which is this. I'm going to subtract row 1 from it and put that answer into row 3. So I'm going to take this row, subtract this row from it, and put that into my new row 3. Okay, so that gives me this right here. Now notice here, now I have zeros all the way down, and I want to get zeros everywhere below the diagonal to put it in an upper triangular form. So I already have zeros down here. Okay, so now I say, okay, I'm going to take row 2 here, subtract 2 times row 3. Here's row 3. Now notice that 2 times row 3, 2 times 2 is 4. So then I'm subtracting 4 from 4, and that puts a 0 into my new row 3. I take 2 times 2 is 4, and I subtract that from negative 2. That gives me a negative 6 into my new row 3. And I take 2 times negative 2 is negative 4, and I subtract that. Negative 4 from negative 1 is 3, and I put that into my new row 3. So here is what I have right now. It's getting there. Here's my diagonal, but I still have a 1 and negative 1 down here. And so in order, and I have, and so I need to continue to work on this. So now I take row 2 and I subtract from row 2 4 times row 4. And I put that back into row 2. So here's row 4. What I'm doing is I see I can put a 0 here. So here's 4 times row 4. 4 times 1 is 4. Subtract that from 4 is 0. 4 times negative 1 is negative 4. And I subtract that from negative 2. And that gives me a plus 2. 4 times 0 is 0. Subtract that from negative 1. I still have negative 1. So this is now my new matrix. Then I exchange rows 2 and row 4. And when I do that, so I exchange row 2 and row 4. So I'm taking this row and just exchanging exchanging them. That gives me this expression right in here. So again, now I'm almost there. I have a 2 down here below the diagonal. And so if I take 3 times row 4, 3 times this row, add it to row 3, and then put it back into row 4. So 3 times row 4, 3 times 2 is 6. 6 plus negative 6 is 0. So that goes into my new row 4. 3 times negative 1 is negative 3. Add that to 3 plus 3, that's 0. And I put that into my row 4. So now I have, not only are all the terms below the diagonal 0, but I have row 4 is entirely 0. So I don't even need that row anymore. So now I look at what I have, and the equations that I have 1 times A minus 2 times C. That's this equation right here. 1 times A minus 2 times C equals 0. I have B minus C equals 0. B minus C equals 0. And right here, I have 1 times A minus, right here, I have minus 6 times C plus 3 times D equals 0. So let's look now. These are the 3 equations that I get by looking at this matrix right here. So this matrix times this vector equaling 0 gives me these 3 equations. Now, for me, I really don't have to continue anymore. I can look at these 3 equations and I can pretty much find my answer in that I see that B equals C. Okay, so that's pretty clear. B is going to equal C. Here are my 3 equations again. So I say that B is equal to C. If B is equal to C, I see that A must equal 2C. And then this is saying if I take this equation here and I divide it by 2, I see that I get negative 3C plus D, or sorry, I divide this equation here by negative 3, and I get that, or divide it by 3, and I get 2C plus D is equal to 0. So these 3 equations I pretty much solve just by looking at them, and I can see that what the solution here is A equal 2, C equal 1, B equal 1, and D equal 2. However, I do have a method which I'll talk about in another video, a subsequent video, of how I can now look at these and I can tell you exactly what A, B, C, and D happen to be. And I do that by looking at the least common multiple of coefficients in the equations. And like I said, I'll talk about that momentarily. So that is my first video discussion of how I use linear algebra, matrix equations, to solve a system of linear equations that I developed by looking at the chemical equation, a balancing problem. Okay, until next time.